Hello, my name is Felix Burmeister. I'm a systems engineer and I'm happily presenting on behalf of our company innolectric. Thank you so much for your interest in our topic. The usage of nanocrystalline soft magnetic materials for high efficient and power density in electric vehicle onboard chargers. We will start with the introduction to the application of our onboard charger. We will discuss our expectations on nanocrystalline soft magnetic materials and why we choose this material after all. We will talk about how we procured different samples for testing, how we tested these, and the results in both technical aspects and economical aspects. First, a few words on our company. Our engineering team has been working since the early 2000s on different projects and topics related to electromobility. Such were motor inverters, batteries for special industrial vehicles. But since 2016, when we worked as an independent company, another focus was on charging technologies, both AC and DC. And the OBC platform with 22 kilowatts was our first product. We have been starting in production in 2020. And after that, also been focusing on DC charging communication. Our company residence in Bochum in the western part of Germany, where we have our own laboratory to both test our hardware and software. So anytime we can offer and supply services and products with a seamless match for software and hardware with this respect in our complete portfolio regarding power electronics, charging communication, and energy storage systems. So our products can be found in a lot of different sectors and a lot of usages, ranging from transportation with vans and trucks through mining, airports infrastructure, anything until electronic yachts and super sports vehicles, any sort of new mobility concept. And all these companies have some form of expectation from us. They want an easy integration because their experience is sometimes not as high. So often they are starting with moving into electromobility and using our product to get a quick start in this. So the product we're going to be talking about today is the so-called onboard charger. Here we see a sample picture of one of the products which is in production from our side. It's a 22 kilowatt AC to DC charging system with both AC and DC charging communication included, a high efficiency of up to 96% and output for nominal battery voltage systems of 400 and 800 volts. So, as you all know, in the automotive sector, the expectations from customers are high. There's cost sensitivity, there's a strict limitation in installation space, and we always must decrease the weight of our products. Any kilogram which our products weigh less is a kilogram more that can be used in transportation, for example. And of course, there's always a demand to boost efficiency. And on the other hand, of course, we have a lot of technical challenges with regard to isolation, high current density, and of course, the strict electromagnetic compatibility we need. On the other hand, we also have an advantage in our customer sector because most of our customers are not only choosing the product on the price for purchase, but for the total cost of ownership. So for the price they're paying to use the product over the complete life cycle, maybe 5, 10, 30 or 40 years. And so one of the components we really never focused on has been the magnetic cores in our systems. And we estimated they can take up about 14–15% of the total weight and also volume of our products. And this is something we wanted to focus on. So let's have a quick view in the schematics, a sample schematic of one of the technologies we had so far. We will begin from the left-hand side. For a three-phase input, 3 phases with each 230 volts. First going onto the filter elements, an AC common would choke. And after that, it's been split up in the individual phases which then go through a PFC grid choke into the PFC main choke, the PFC inductor, and after that being rectified into a DC link voltage in between 0 and 1000 volts. So here on the input side, so far, we built the PFC choke ourselves. But for the AC common mode choke, a 4-phase system, and the AC grid choke of 1-phase system, we have always been using off-the-shelf products we could easily get from suppliers within the European Union, which were not produced specifically for, which were not specifically being built for us, but were off-the-shelf products. On the DC output side, we come from the DC link voltage, go through the inverter, or something like an H-bridge or full bridge not shown in the picture. We go through the LLC inductor into the rectification, and then the main filter element is the DC common mode choke, where we are already on the level on the output voltage of 400 or 800 volt up to 1000 volts DC. And also here, the LLC transformer was something we built ourselves, but the DC common mode choke was also been a product we just bought directly online. So, and this is going to be the base solution which we are going to be focusing for this presentation today. We're going to look into this DC common mode choke further on. So as we were thinking about, okay, how should we start? What technology should we focus on? We came in contact with a company called CBMM. CBMM is based in Brazil, but also for example, has a representative office in China. And we learned that for the last 60 or so years, they have been the biggest supplier worldwide for a material called niobium. And niobium is a key component used in nanocrystalline soft magnetic materials, which we until then never heard about. And so CBMM is on the far other side of the supply chain. So they are supplying raw materials, and they are helping different companies with developing the niobium-based products in all sorts of application in infrastructure, mobility, aerospace, health, and the energy sectors. And so they were interested in looking into the problems we as a company doing the application of such products. They wanted to know, like, what difficulties do we have in procurement, design, and application, and how they could help out. And we, on the other hand, of course, were interested in this technology. So since then, we have been in a cooperation on this topic. So what were our expectations on this material? The material properties, which are then being shown, are high permeability, low coercivity, low magnetostriction, high Curie temperature, high saturation flux density. What does that mean for us? We were told that we could expect advantages in a range of up to 50% reduction in weight, 75% reduction in size, a wider frequency range for damping, which of course is really relevant for electromagnetic compatibility, also improved damping at lower frequency in the range of several kilohertz, an operational temperature higher than those of typical ferrites, up to 130 degrees Celsius, and the possibility to improve the overall efficiency of our design. And out of that, there are, of course, some design advantages. So with the high permeability, there is a less number of windings necessary, so we can ease installation. Also, with the wider dampening, we might reduce the amount of devices we need for filtering. Maybe not in a simple design we've been showing before, but maybe in a more complex design. And as I said, with the higher temperature and the easy installation, we might also be more flexible in the cooling system. So these are a lot of advantages we are interested in. And so we selected nanocrystalline soft magnetical, in short, NSMM, as something we want to focus on. So what did we do to get our hands on such materials? So we said we wanted to be as easy as possible for us. We want to use the same PCBs as before, and we would just want to swap out one-to-one the previous samples with alternative materials. So we just looked out for companies which openly online advertise their knowledge in nanocrystalline soft magnetic materials. And the only thing we presented to them were just a quick notes. So we would supply to them a data sheet of the component we have been using so far, some basic numbers such as the number of phases, inductances from the data sheet, temperature ranging, voltage and current levels. But we didn't say something specific about like how we wanted it to be optimized. So we just said to them, this is a component we have been using so far. Do something with nanocrystalline magnetic material and show us what you got. So a multi-criteria problem, which we just passed on to different companies. And so what has been our experience so far? All companies which we came in contact with were able to supply the sample to us within 4 to 8 weeks. All had really good quality and all were some good prices, ranging from sometimes just $2 per piece until maybe $50 or $100 per piece maximum. So that was quite all right. And they usually just had 2 questions. One question was, of course, the production quantity. So we typically gave them a number of 5,000 pieces per year so we can compare them. And the other questions was really always, why are you interested in nanocrystalline soft magnetic materials? You're working in the automotive sector. Are you sure about it? Because most of other customers we've been having so far, they only focused on the total price. And we always had to say, no, please focus on NSMM material. We really want to go into it. So, as I said, we're going to focus just on the DC common mode choke because we don't have that much time. Here on the far left, you again see the DC common mode choke we have been using so far. And on the right, the 3 alternatives that were supplied to us during the project phase. Alternative 1 is coming from a company from North America, a company that is focusing on prototyping to smaller series, maybe in a range to several hundred, maybe a few thousand pieces per year. And the other 2 alternatives come from mass producers from the Asian continent. So now here we have the comparison between a casual ferrite component to nanocrystalline. And you can already see from the pictures that there is a huge difference between sizes and weight. So we go from something nearly 200 grams down to something as low as 50 grams and a really huge decrease in sizes. We later on come on to like a percentage perspective on that. So how did we want to test? We determined 3 phases. We were starting with the determination of the electrical characteristic, RLC values and the resonance frequency, so we could see if the components match our goals, our parameters we were giving to the companies. We then continue with the validation of functionality under full load, so under full stress, minimum and maximum output voltage and maximum output currents as well. And we wanted to see how the power dissipation looks like, how their thermal behavior looks like, everything to see if it is really working on a long time under all conditions. And the third part, of course, was to check on electromagnetic compatibility. So the possibilities we have in our own laboratory is to look into wired connections, wired interference. So what were some of the general findings we had when we started with looking for LC values, etc.? So we saw that all of the components supplied to us had a wider frequency range. They had a wider range of resonance frequency, typically 20 to 30 times more. So, for example, 16 megahertz for the nanocrystalline material to only a half megahertz of the ferrite component, which indicates a good quality in the damping over a longer range of frequencies. All of the components also had higher inductance values, which also came to our surprise. So, as I said, we supplied data sheets with the minimum inductance levels, for example, for 1, 10, and 100 kilohertz. And for example, at 10 kilohertz, values were in between 20% or to 90% higher. And also something we measured, of course, of the low amount of windings were lower parasitic capacitance, typically by a factor between 10 to 1,000. So let's look into the numbers. We start with the volume, just the volume of the core compared to that of the current solutions. And we see again that there is a huge difference, up to 63% reduction in size of just a magnetic core. And then we see weight, where also, for example, alternative 3, which wasn't that much reduction in size, but was also really good in. So in between 40 to 70% less weight of the complete component with base plate and, of course, windings. So there where we see that nanocrystalline materials show a significant benefit in all mechanical properties. And as I said, only alternative 3 was maybe not that good, but when we take a look at like the inner diameter, it also suggests that there might be a possible optimization there. So that's it for the mechanical properties. Now let's look into the electrical. So something you might expect is, of course, what do the losses look like? So the power dissipation. And here we are not looking at the best numbers, but really at the worst numbers. So these numbers were taken at the highest output current with a really much high output voltage as well. So here we see that all the components were at least as good as the common part used before, but they were typically in between 5 and 27%, even better. So 27% less power dissipation, a really good number. And we were able to evaluate and check that this is really true, that there's not a wrong measurement, because we also looked into the temperatures. And all components were on really the same level, even after several hours of testing, and only reached temperatures around 90 degrees. And were always cooler than the common mode choke we previously used. So now we come to the last part, the electromagnetic interference. And here the results are a bit more mixed. So for example, alternatives 2 and 3, that seems to be like a correlation between when the losses are lower, also EMI is on the other hand a bit more worse. But when we look at alternative 1, even this component was behaving much better. And again, this is at the most challenging point. So here we are looking at the attenuation in decibels at the most challenging point, the LSD frequency in the range of around several hundred kilohertz. So even there was at least one alternative with a better behavior. And of course, we have to see, we only swapped out the component directly. We didn't change anything to the PCB. We didn't change anything to resistance values, capacitors, anything correlating with the schematics. So we might think, of course, that when we would spend more time and make maybe smaller changes to the winding, smaller changing to the layout of our filtering, that we maybe could even level out these disadvantages. So how about economical aspects, of course? So, of course, one of the things we've been told at the beginning were that we might have to expect that, of course, the price is going to be higher. And so we are starting with the current solution. It has a price range about maybe $8 to $10, €8 to €10. And in comparison, alternative 1 was much pricier, around like $20 or $30. But again, as I said, alternative 1 is coming from a supplier which focusing only on smaller amounts of production. So for 5,000 pieces a year, but they would have to set up a complete new production site. So this is, of course, the main reason for them that they're more price expensive. But actually, to our surprise, alternative 2 and 3 were much lower in price. So alternative 2 maybe in a range of $2 or $3 a piece, and alternative 3 in the range of maybe $3 or $4. So it turns out to us that the biggest impact on the price is actually not really the material, but really like who is supplying these components and how are the development and production costs. But then again, okay, of course, when we go just one supplier, there might be a difference between the ferrite component and the nanocrystalline soft magnetic component. And so, for example, we asked the supplier of alternative 3, what do you think? How much difference would have been? How much difference does it make for this component to be soft magnetic material? And they stated that it would be probably about double the price of the ferrite alternative. So maybe $2 difference between ferrite to nanocrystalline materials. And now, as I said at the beginning, our main focus is on the total cost of ownership. And we want to give a really, really simple calculation about like how might that look like when we compare ferrite to nanocrystalline material. And we're going to look in just one simple exemplary calculation on just only a focus on the power dissipation. So let's take a simple example. We take a small delivery van, which is going for 250 kilometers a day, 300 recharges a day for a 16-year lifetime. And now we'll take a look like how expensive is a DC common mode choke in total cost of ownership for the lifetime. And we come to a point where we calculated that this component dissipates about 50 watts of power under full load, 22 kilowatts, so about nearly a quarter of a percentage point of the overall efficiency of the device. And we come to the point of an estimation that this component alone costs about 10 euros per year. So 160 euros or $160 over the complete lifetime of this vehicle. So let's compare this to nanocrystalline soft magnetic materials. So as I said, maybe we estimate with $2 more. Now we come to the point that we saw, okay, they are even 5% to 27% more efficient. And so when we go just to the cost of energy, that would save us something in between, like 5% or 27% of these 10 euros per year. So we come to a break-even point just after 1 to 4 years that the total cost of ownership level out the higher cost for the samples. And as I said, this is only the focus, of course, for the total cost of ownership for the electrical losses. So as I said, we had the great benefits as well in the size comparison and the weight, and also sometimes electromagnetic interference. So for some special applications where size and EMC electromagnetic compatibility is really important, we might even see that alternative 1 would maybe be the better alternative compared to the current solution at some points. But as I said, alternative 2 or 3 that are so low in price, we really estimated, okay, this is a really huge benefit. And this is, of course, the outlook for us. With this project, we really saw, okay, the nanocrystalline soft magnetic materials has a huge impact of a strong optimization for our onboard charger. So reduction in size, reduction in weight, and no sacrifices to efficiency and EMC, and possibly even there are some optimization potentials. And so we come to really unique selling points for our customers. So and as we saw, we really don't need that much expertise when we go to different companies on selecting them. But really the biggest thing we have been seeing, our biggest experience, and something we want to tell you is really it is important to really compare different components and really test them on a system level under full load. Because as you're seeing, there are huge differences in the materials and what might be supplied to you. But then, after all, the outlook for us is, of course, we are going to continue to be working with alternative materials such as nanocrystalline and soft magnetic materials, because we see that there's a huge improvement over the current state of art with ferrite components. And this is something we're going to continue for all the projects we are doing at the moment and in the future. And well, maybe also a project in the future we might do with you. So thank you so much for your interest. Thank you so much for your time. This has been everything from our side. If you're interested in getting more information, if you're interested in getting in contact with us, please don't hesitate. Down below in the picture, you are seeing the QR code for our English website to get in contact with us. And of course, you're seeing everything from the mail contact and numbers down below. So again, thank you so much and goodbye.